Okay, so we've seen how linear momentum, the conservation of momentum that we talked about before, really had to do with Newton's first law. And we can see that there's obviously some kind of connection between angular variables and linear variables. And so now we're going to see how we can connect angular momentum and linear momentum, and how the conservation of linear momentum is really just a special case of a conservation of angular momentum. Okay, so let's say we have some point, and we'll just call this point our axis of rotation. Okay, so if we have some particle out here and it's moving with a velocity v, okay, then we have a vector r that goes straight from our axis of rotation to that point. Another way that we can write angular momentum is we can say that L is equal to r cross p, where r is the vector that goes from the axis of rotation to that particle, and p is the momentum, so mass times the velocity. Okay, so I should have written that as a vector. So again, since we're talking about a cross product, okay, so the magnitude of L is equal to the magnitude of r times the magnitude of p times sine theta, where theta is this angle between the two. But now let's take a look at several different time steps. Okay, so once again, we'll set a point here, and this is going to be our axis of rotation. Okay, and we're going to have a particle traveling to the right, and we'll look at it at a few different times. Okay. So we'll call this R1, R2, and R3. This will be, we'll say that it's always moving with the same velocity v. And we'll call these angles theta 1, theta 2, which is 90 degrees, and theta 3. Okay, so now let's look at the angular momentum at all 3 points. So for the first point, okay, we say that L1, the magnitude of L1 is going to be the magnitude of R1, magnitude of V, times sine theta 1. And then we see that L2 is equal to R2 magnitude of V sine theta 2. Well, the sine of theta 2 is 1 because this is 90 degrees. So L2 is really R2 V. Okay? Well, but let's look at L1 again. This is R1 sine theta. We notice we call this angle theta. So R1 has two components. We have an x component, which is R1 cosine theta, and we have a y component, which is R1 sine theta. Well, R1 sine theta, this vector, the magnitude of this is exactly the same as the magnitude of R2. So in other words, R1 sine theta, this is equal to magnitude of R2 V. So L2, the magnitude of L2 is equal to the magnitude of L1. So, and because these are all in a plane, that we see that L2 is actually equal to L1. So in this case, momentum P is equal to mv is conserved, and angular momentum, which is r cross p, is also conserved. It's, in fact, it's basically, it's the same thing, right? It's momentum. Sorry, these should have all had a factor of m in them, right? So angular momentum just has units of a momentum times a distance. So anytime momentum is constant, it also tells us that angular momentum is constant.